Okay, so you've watched the video now on chemical equivalency, and you've also looked at multiplicity. Okay, so you've had two Khan Academy videos there to watch as well, so please do make sure you have watched them because they give a really lovely explanation of the two. So just to summarise, okay, so our multiplicity is what we call the appearance of a group of symmetrical peaks representing a hydrogen or a group of equivalent hydrogens in our NMR spectroscopy. Typically we're going to see them as singlets, doublets, triplets, quartets, quintets, or sextets, etc. Okay, so this just comes from our Pascal's triangle here, and like that we'll see their shapes, okay, or the shapes of their peaks and what they look like. Okay, so a singlet is just going to be one distinct peak. A doublet we're going to have two peaks of equal height. A triplet will have two smaller ones on the outside and one taller peak in the middle, and so on and so forth. Okay, now what does multiplicity do? Well, multiplicity tells us information about our neighbouring hydrogens. Okay, so here we just have the structure of ethanol. Okay, so we have CH3, CH2OH. So if I was looking at the spectrum from the very beginning, what I'd do is I would look at the chemical structure and I'd begin to determine how many equivalent hydrogens I have present. Okay, so I'd look at each hydrogen and I'd see what is surrounding on either side. Are they in the same chemical environments? So if I look at this methyl group on the furthest left here, so I have one carbon and it's bound to three hydrogens. These three hydrogens are all equivalent because all three of them are bound to one carbon that is neighbouring another carbon that's bound to two hydrogens. Okay, so these three become known as equivalent. They are the same, and therefore we're only going to have one peak representing all three of these hydrogens. The next set of hydrogens we have a carbon bound to two hydrogens, and these hydrogens are directly neighbouring these three hydrogens. Okay, but these two hydrogens themselves again are in the same chemical environment because they're beside a methyl group and an alcohol group. So therefore these two are the same and are going to be represented by one peak. And then finally we have the hydrogen beside our oxygen here. Okay, and this is by itself, so it's going to have one peak by itself. So then, if I have three groups or three equivalent hydrogens essentially, then I'm going to have three peaks. And we can see in the spectrum that I do have 1, 2, 3. We do have splitting within some of these peaks, and that gives us information about the neighbours. Okay, and here we use the n+1 rule. So let's say we have our three carbons or three hydrogens here. Okay, first thing to note is right beside them we have no electronegative groups or no electron withdrawing groups. So this is going to be pretty close up to 0. Okay, so there's a good chance that this group is going to be it. What other information will give us, can help us confirm that it is that methyl group? Well, we look at the splitting of this peak. So we have 1, 2, 3. We have a triplet, and again, following our Pascal's triangle, we can see the ratio. So we have two smaller peaks on the outside and one larger peak on the inside. Okay. From our n+1, so we say n+1 is equal to 3 because we see 3 peaks. So therefore, the number of neighbouring hydrogens beside it must be 2. Okay, and that makes sense because when we look at the number of hydrogens beside this methyl group, we do in fact have 2. So it's a good guess that this is going to be this methyl group here, or else just we call it A. Okay, if we look at the next peak, so around 2.5, we just named it B here. Now, in this spectrum, you have been told that you have 2 hydrogens, 1 hydrogen, 3 hydrogens, etc. Sometimes you won't be given that, and you still have to be able to determine or roughly approximate what is what and why is it what you've said it is. So B, if we're using your n+1 rule, n+1 equals 1 because we just have one peak. So n must be 0. So that must mean that there is 0 neighbouring hydrogens. So when we look at this structure here, the only proton that doesn't have an immediate neighbouring hydrogen beside it is this hydrogen of our oxygen group. Okay, so this is immediately bound to this oxygen, but this oxygen has no other group bound to it, most certainly no other hydrogens. So therefore, this smaller peak here is our hydrogen on our OH group. And then finally we have this here, so we have a quartet. So 1, 2, 3, 4, 4 peaks, quartet. Using our n plus 1 rule, we'd say n plus 1 equals 4, so therefore n must be 3. So therefore we have 3 hydrogens in our neighbouring group, and again that corresponds to what we actually have immediately beside our structure here, or immediately beside our CH2 group. Okay, so that's us using our multiplicity, using our splitting of our peaks to obtain additional information. Another piece of information that we typically can use is our integration, okay? So we integrate our peaks when we're in the lab. So we run our spectrum and we begin to do our processing, and part of our processing is our integration, okay? And the integration is basically correlating the height of our peaks to the number of protons that's going to be represented by that peak. Okay, so our integration tells us the number of hydrogens that peak represents. So typically we're going to see it as the integration sign, or an S sign, okay? And again, it's just measuring the area under the peak, and it'll give rise to how many hydrogens that peak represents. So if we look here, again, you'd go through the process of identifying your equivalent hydrogens, how many groups you're going to have, therefore how many peaks you're going to have. So here we have 2 distinct groups of equivalent hydrogens, A and B. A, we look at what is immediately bound to it, so A is bound to a more electronegative group, so therefore it's going to be further afield, and B is going to be closer to 0. And then we'd use our integration, and we'd find out that A represents 2 hydrogens, B represents 3. And then we'd also be able to look at our peak splitting to tell us about the neighbours, okay? So again, B, or if we looked at A, for example, we would have our n plus 1 rule, okay? So number of hydrogens is 3, so n would be 3 plus 1. So for A, we should see a quartet, okay, so 4 peaks. That would tell us that's beside 3 equivalent hydrogens. Same for B, okay, B is beside a CH2 group, so our n plus 1 would be 2 plus 1, which will give us 3. So we should see a triplet here for our B. If we look at ethanol again, we can work through our structure. So in our ethanol, we have our 3 distinct peaks, okay? So we have a peak for a CH3 group, a peak for a CH2 group, and a small peak here for our hydrogen on our oxygen, okay? Now, with our OH groups and with NH groups, they're not set in stone. They can definitely flip around and move around depending on the solvent we're using. So just be aware of that, because if we look at the peak, or the spectrum here, we've been told that our oxygen is around 2.5. But here it's down around 4.5. So just keep that in mind. That does depend on the solvent that has been used. But nevertheless, the trend remains the same, okay? And our multiplicity here remains the same. So we said we had a CH3 group on the end here. We said that is furthest away from the electronegative group, therefore it's going to appear closer to 0. That is still true. When we apply our n plus 1 rule, we said, well, this CH3 group is beside CH2. So 2 plus 1 will give us 3, so therefore we should see a triplet here, which is what we do see. When we talk about our CH2 group, it is directly bound to an electronegative group, so therefore it's being pulled further downfield. Its neighbour is a CH3 group, so we go back to our n plus 1, so 3 plus 1 equals 4, so we should see a quartet, which we do. In our instrument then, we would just integrate it, okay? And we'll go through this in the online lab next week, okay, so how we actually go about integrating this, because the instrument will do an automatic integration, but it's not always true. So we typically need to normalize our integration ourselves just to a peak that we know for certain is either representing 1 hydrogen or 2 hydrogens, one that we're very, very confident of, and then everything else will be integrated in relation to that. With our OH group, okay, so again it's a singlet and it's a really broad one, so that's really characteristic for OHs and NHs in particular. And again, we see it's a singlet here, and that makes sense with our n plus 1 rule, because that hydrogen is bound to an oxygen with nothing else beside it, so therefore we 0 plus 1 will give us 1, a singlet, which we see. Okay, so all of our integration then makes sense because we've told we have 1 hydrogen, 2 hydrogens, and 3 hydrogens here. So we have 6 total, which if we add up all our hydrogens in our ethanol here, so 1, 2, 3, 4, 5, 6. Okay, so that makes sense. So we can get loads of information here from our NMR spectrum. So again, it is the only means that we've used so far that we can actually get that much detail. What if we look at some active pharmaceutical ingredients? Okay, so we have our paracetamol, and we have a structure up here. So again, in this one you can see now that we don't have integration, but you should still be able to determine what they are based on their chemical shifts, based on any splitting, that kind of thing, okay? So we should get used to being able to predicting our spectra. So first of all, we have paracetamol, which is also known as acetaminophen. We have an isolated CH3 group or methyl group at 2.07. This is pulled a little bit further downfield simply because we do have a more electronegative oxygen beside it. Okay, so that's just pulled it down a little bit more. These hydrogens are de-shielded, okay, so they experience the full power of the magnetic field a little bit more. We then see 2 doublets. So again, in practice in the lab, our doublets aren't always perfectly distinct. We do have to be able to, I suppose in the lab we could definitely zoom in on them, but just be warned that they're not always super crystal clear. But we have 2 doublets at 6.72 and 7.3 parts per million. Remember, in this region, we are now in our aromatic region, so we do already know that they're going to be associated with these. Okay, so the hydrogens on each of that benzene ring. But how do we know which ones, okay? Well, again, we have to consider the electronegativity of the groups. So B1 and B2, okay, so those represented by the B peak here. They are bound to a carbon, which is bound for nitrogen. So this NH group is definitely still going to be impacting these a little bit. The carbon here, or sorry, your C's, they're going to be bound to a carbon, which is bound to an oxygen. And oxygen is just that bit more electronegative than our nitrogen, okay? So these are probably going to be de-shielded a bit more, so pulled further down. So it would make sense that our protons that are bound to a carbon, that are beside a nitrogen, are going to be a little bit closer to 0 than our protons that are bound to a carbon, bound to an oxygen. Okay, so we're considering our electronegativity of these groups here. And then we have 2 more hydrogens remaining. And again, these 2 peaks actually may not always appear. So with our NH and our OH, these protons are obviously massively de-shielded due to the highly electronegative groups that they're bound to, so your nitrogens and your oxygens. So they're pulled all the way down, close to about 9 and 9.7 respectively. So they've been pulled the whole way down. These peaks do not always appear. It depends heavily on the solvent that you've actually chosen to run. So for example, if we used CD03, so if we had methanol here, we would find that these groups don't appear at all because you get a deuterium exchange. So what we'd see is we'd see our methanol peak, but we would not see these groups. So depending on the solvent, they may or may not be present. What about the spectrum of aspirin? So our structure has gotten a little bit more complicated, and we can see we have loads of information going on, so much so that we've had to zone in on our aromatic region, and we see lots of splitting here. So again, we work through the exact same way. So the first thing is I look at my structure. I want to identify what hydrogens are present, how many, if any of them, are equivalent, because this will tell me the number of peaks I should have. So straight away I know that this group, the CH3 group by itself, is going to be by itself. Okay, so I'm going to have 1 large peak for this. I'm going to have 1 peak for the hydrogen bound to this carboxylic acid. It's going to be really small and it's going to be really far down because it's bound to such an electronegative group. Usually with aromatic groups, we'd start to think that those on the opposite sides would be equivalent, but this is not the case in aspirin, because we look at this hydrogen here, okay, this proton, it's beside another CH group, but it's already beside a carboxylic acid group, so this is going to be by itself. This hydrogen here is beside a hydrogen and beside a hydrogen, it's going to be by itself. This is also beside two hydrogens, but those two hydrogens are already influenced by different chemical environments. So this, again, is going to be by itself. And the same here, this hydrogen is beside a carbon, a C single bond O group, and a CH. So again, it's going to be by itself. Okay, so all of their chemical environments are different. And because of that, we have 1, 2, 3, 4, 5, 6 peaks. And we see that we have a very tiny one here, and good guess what that already is going to be. 2, 3, 4, 5, 6. So that corresponds to how many different hydrogens or different protons I think we already have. Okay, so again, F, we can say it's our CH3 group. It's pulled down a little bit further because of this carboxylic acid, so really electronegative. And we can also see how much taller it is than everything else. Okay, because this is it's supposed to be 3 times more intense than all of our other groups because it represents 3 hydrogens, whereas the rest of these really only represent 1. A, again, a good estimation is that this is going to be the hydrogen on our carboxylic acid group. Okay, really, really de-shielded, pushed all the way down, and typically going to be a tiny little hill, really, not a sharp defined peak. And then we're in our aromatic region. We can see that's far more complex because this time we don't have any, we don't have 4 equivalent groups. We have 4 groups that are in entirely different chemical environments. So if we start up here around 7.2, okay, we have a doublet here. We have E. So again, our doublet is equal to n plus 1. So therefore, we're saying that whatever proton this represents is beside 1 hydrogen. And that makes sense, okay, because E here is beside an oxygen, so that has no other hydrogens on it. And on its other side, we have 1 hydrogen, so that makes sense. At around 7.3 and 7.35, we have a triplet. Okay, so that's D. So D here, again, if we use our n plus 1 rule, so n plus 1 is equal to 3, because we see 3 peaks. So therefore, whatever peak this represents, it must be beside 2 hydrogens. And again, that makes sense, because D here is beside 2 hydrogens. C, again, represented by a triplet, so n plus 1 equals 3, so neighbouring to this peak must be 2 hydrogens. So we said C, so again, that makes sense, because this hydrogen is beside 2, so 2 hydrogens, that makes sense. And then finally, B is represented by a doublet, so 2. So 2 is equal to n plus 1, so n must be 1. It's beside 1 hydrogen or 1 proton. So therefore, again, that makes sense because this hydrogen is bound to 1 carbon that has 1 hydrogen. But this group, okay, obviously the way we have it represented here, it looks like this hydrogen is directly beside it, but it's not. It's a few bonds away. So this hydrogen is beside 1 hydrogen here. So again, that makes sense. So that's how you typically go about analysing them. There's a few bits and a few steps involved. So again, identifying your equivalent groups, seeing how many peaks they represent, making sure that that is in agreement with your spectrum, and then starting to look at your kind of common areas. So again, your alkyl area, your aromatic region, do you have any OHs or NHs? And then starting to look at your so where you think they typically fall in line, and then looking at your peak splitting, and then just working your way through assigning them, okay? And again, remember with your OH, depending on the solvent that we run it in, we may not see that OH group. So I'm going to ask you guys to just give this a little go yourself. So determine the shifts or determine the NMR spectra that you would see for each of these molecules, and I'll leave the answers at the end of the lecture notes, okay? So just give it a go yourself. We talked about proton NMR, but we can also have carbon NMR. Okay, and the isotope of interest is the carbon-13 isotope. However, the abundance of carbon-13 isotope is only about 1.1% of that of the regular, carbon-12. So therefore, carbon-13 signal can be very weak. So you'll find for this reason we typically have to use a larger amount of our samples if we want to get a carbon-13 spectrum, okay? So carbon-13 spectrum will give us additional information. It will help confirm our proton spectrum. But we do have to make sure that we have enough samples to do it. We have to make sure that our solubility of our sample is good enough, because we want a high quality spectrum. Because the spectrum or the carbon-13 NMR can be a little bit weaker, we do actually look at it on a longer range or a broader range. So your carbon-13 spectrum is typically going to range from 0 to 180 parts per million, whereas your proton NMR is typically going to be from 0 to 14. And again, the same trends follow, okay? So we still do have similar chemical shift values. So we still have our alkyl region. We still have our alkyl regions that now have more electronegative groups bound them. So, oxygens, nitrogens, double and triple bonds. We then have our aromatic area, and again, we might get some nitrogen or NH groups popping up here too. And then we have the carbons that are immediately bound to more electronegative groups. So halogens, nitrogens, oxygens, etc. Okay, so again, it is important that you're aware of these trends in chemical shifts for both proton and carbon NMR. So this is an example of a carbon-13 NMR spectrum, and this is just a folic acid, okay, so the B vitamin. And straight away, what you should notice is there's little to no splitting, okay, little to no multiplicity, and there's no integration. So in an NMR spectrum for carbon-13, we typically do not have integration and we don't really have multiplicity. We are just getting individual peaks, okay, so we're really just looking at chemical shifts. And obviously, in a carbon NMR spectrum, we are no longer looking at the hydrogens, we are looking at the actual carbons, okay. So again, if you had a carbon-13 spectrum, you'd have your structure that you think it is. Okay, so if you're doing chemical synthesis, you'd have the structure of the molecule you think you've made, you hope you've made, and you'd literally go through and you'd identify every carbon. So again, just for your knowledge of chemical structures, so this is our skeletal structures, another way to draw a chemical structure. So every corner is a carbon. Okay, so we literally go through and number and label all of these carbons. And again, you start to take note, what are those carbons bound to? Okay, so we have carbons that are bound to oxygens, and we have carbonyl groups, we have amide groups, we have aromatic regions, we have lots going on, and all of that is going to influence the chemical shift or position at which we're going to find them. So again, the regions are still fairly similar. Up here, okay, so I'd say between 10 and 6 or 0 and 60, you're going to find just your alkyl groups, okay, so CH2s and CH3s that are not bound to any particular electronegative groups. You're still going to have an aromatic region, and you're going to have the region then that you have carboxylic acids, you're going to have amides, amide bonds, that kind of thing. Okay, so those regions still hold up from our proton NMR. But again, this is a fairly complex structure. This is a fairly complex spectrum. Okay, and again, we may actually find, because carbon NMR is not as sensitive as proton NMR, we might actually find that we still have some peaks even missing. And if we look on our y-axis, we can see that we're only down around 17% intensity, okay? And this is because we've literally had to amplify these as much as possible to try and find even our smallest peaks. But there's obviously trade in here, because the more we amplify, okay, the more we zone in on the spectrum, we also increase the noise. So we can see our baseline here is really, really noisy, okay? And this is possible with carbon NMR. So it's, again, just something to be aware of. We typically will have a noisier baseline, when we're dealing with samples that maybe aren't fully soluble, maybe it's a little bit too dilute, or maybe like that we just think we're missing some peaks, so we've zoomed in a little bit. So there are other ways we can try and get a bit more information out of carbon-13 NMR spectrum, and this is called distortionist enhancement by polarization. So this is our DEPT, and DEPT can help us just classify some of those peaks that we're seeing. So they can classify and distinguish between a CH3 group, a CH2 group, a CH group, and also we can have ones that just tell us about a quaternary carbon. Okay, so just a carbon by itself. So how this works is the proton pulse is literally just set at 45 degrees, 90 degrees, or 135 degrees. These are all in 3 separate experiments. So if you were to use an NMR instrument, this would have to be specifically set up, and you'd run each of these. So depth 45, depth 90, and depth 135, and we would get different patterns, okay? So if we looked at a regular carbon-13 spectrum, they would give us carbons, CHs, CH2s, and CH3 groups, and they'd all be in an upward position. If we ran at depth 45, we would find that the information we're given, we no longer see carbon, quaternary carbons, but we do see CHs, CH2s, and CH3s. Depth 90s will only show us CH groups, and depth 135 will have two planes, okay? So we'll have CHs and CH3s pointing upwards and CH2s facing downwards. And you'd use all of these together to start building your picture of your structure. And again, you'd already have an image from your protons, but this again is confirming and building our idea of your structure. So again, we could look at it as an example, okay? So these again are folic acid. So we'd have our plain old carbon-13, so again showing us quaternary carbons, CH groups, CH2s, and CH3s. And you can see already that it is a relatively weak signal, okay? And that primarily is due to folic acid being a little bit less soluble. Okay, a compound that's less soluble, okay? But what we can start doing is we can start running our depths. And with our depths, we'll find, as I said, with depth 45, we have a CH, CH2s, and CH3s. So when we compare our depth 45 to our carbon-13, we can start to determine by process of elimination where our quaternary carbons are. When we run our depth 90, we confirm where our CHs are. And when we run our depth 135, we have definite clarification of our CHs and CH3s because they'll be facing upwards, and our CH2s will be facing downwards, okay? And they're all obviously going to be appearing at the same chemical shift, okay, all along our x-axis. So this is a lovely technique to really, solve the puzzle of what your structure is. Another technique that we can use is two-dimensional NMR spectra. So there's lots of different forms of 2D NMR spectra. And these show correlation between carbons and protons, protons and protons, carbons and carbons, etc. The two really commonly used types are HSQC and COSY. Okay, so HSQC stands for heteronuclear single quantum coherence, and COSY literally stands for correlated spectroscopy. And we're just going to look just briefly, just to give you some insight. Okay, so they're 2D, okay, so we're on two axes here. So on our y-axis here, we have our carbon-13 spectrum, and on our y-axis here, we have our H or proton NMR. Again, we can see in our carbon-13, we have no multiplicity and no splitting. Okay, we literally just have our chemical shifts and the relative intensities. And then for our proton NMR, we have got our chemical shifts, we have our relative intensities, and we also have our splitting. And we can basically, what happens is we have a plot like this, and we can correlate. So we correlate this peak here, we go across, we find, so this is what you'd be given in your spectrum. You find a peak of interest and go up, and you can say that this peak here correlates to this peak here. Okay, so this carbon here is related to this proton here. And you do the same for all of them. So again, We go across until we hit a peak and go up, and we can find the proton that it correlates to. And this helps us determine our structure of interest, okay? So this is our HSQC spectrum of aspirin here, okay? So again, we can look and see if we can find a peak of interest. So what do we have? We have 4 here. So 4, we have a triplet, okay? So we know that's going to be beside a CH2 group. We go across and we find our carbon here, okay? So this is just telling us that carbon here, we're going to have, and that makes sense actually, because we have, it's not a CH2 group, but it is beside 2 hydrogens. So our group here is group number 4. So from our proton NMR spectrum, we can say that it's beside 2. That makes sense. And we can now say that this peak here, okay, so this carbon peak corresponds to this proton peak. Okay, so it just gives us a bit more information. We can also compare proton to proton. So again, this is of aspirin. And again, these are the type of peaks you get. So you can go across, you can find out what they correlate to. And it's just another nice way of confirming your information. Okay, so NMR spectroscopy, there's loads of interpretation with it. What I'll do is I'll put up some examples of spectra and see if you can determine the structures. And we'll obviously be going through this in our online lab next week as well. So just before we wrap up, we look at their applications and we look at the strengths and the limitations of NMR spectroscopy. So NMR spectroscopy is a really, really powerful technique. And again, it's the only technique we've covered that can allow us to solve a structure from beginning to end. And because of this, we can determine and characterize the exact structure of raw materials and finished products. We can also use it to determine impurities, because obviously we can find peaks in there that maybe shouldn't be there. And we can use it also to determine enantiomeric impurities, okay? So again, that's talking about groups with different chiral centres. And we can do this without separation, so again, that's really, really impressive. You can do that down to a contamination level of about 10%. And finally, there is potential there for quantitative analysis of drug formulations. So again, typically we look at a lot of these techniques as, particularly with IOR and NMR, as qualitative, but we can do some quantitative analysis. So our strengths and our weaknesses, okay? So our strengths, it provides far more information about molecular structure than any other technique. So we can already see the information we got today. We wouldn't get that from UV, we wouldn't get it from fluorimetry. We get some of it from IOR, but not a whole lot. But we do have limitations here, okay? So it is a relatively insensitive method. So therefore we need at least 5 milligrams to get a good proton NMR, and a 20 mg to get a carbon-13 NMR. And again, if you have a highly valuable compound, if you have something that's very expensive, something that's taken a really long time to make, 20 mg can definitely be a lot to give up for this, particularly since it may not be recoverable depending on the solvent that you have used to run it, okay? So if you have a highly volatile solvent, something like acetone or something you can boil off, like methanol or ethanol or water, maybe, okay, you might be able to get it back out, but you have something like DMSO, you may not be getting that compound back out. The instrumentation itself is expensive, and typically you need to have a dedicated operator for it. So a technician who knows all about NMR, who is capable of running things like depths like COSIs, HSQCs, and anything that may be a bit more technically advanced. There is increased automation, which is great, but definitely you always want a technician or an operator who knows what they're doing with an NMR. So that is all for NMR spectroscopy. So go through those and have a look now at the simulations. So there's a few simulations uploaded there for you from Learn Science about how to prepare your sample, how to run a sample, and like that, interpreting some of the spectrum. So if you do have any questions in the meantime, just drop me an email.